Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about effective mass of an electron and density of states. In this lecture video, I will discuss about electrical conductivity in metals and semiconductors. So let's get started. The content of this lecture video is electrical conductivity in metals and semiconductor. So let's discuss these 2 points in detail one by one. First of all, let's try to understand what is electrical insulation. Generally, fine ceramics, also known as advanced ceramics, are insulating materials that do not conduct electricity. A few examples of products that utilize the insulation property of fine ceramics, which includes the packaging of surface-mounted electronic components such as quartz crystal oscillators and surface acoustic wave filters. These products are widely used in mobile phones, automotive navigation systems, and portable music players. Ceramic packages provide advanced hermetic sealing and electrical insulation between electric circuit lines to maintain the high reliability of these electronic components. So electrical insulation, a material that is unable to conduct electricity due to high level of electrical resistance, is an insulator. In contrast, a conductor is a material that offers low resistance to electric conductivity. An atom, the smallest unit of matter, is composed of a nucleus and electrons which orbit that nucleus. Whether a substance is an insulator or a conductor generally depends on the number of free electrons it possesses, which can be used to carry electric current. A substance with higher insulation properties is less conductive because it possesses fewer free electrons. In addition to fine ceramics, other insulators include paraffin, rubber, plastic, paper, and marble. Because ceramics are fired in a kiln, they can be fashioned into a wide variety of shapes with excellent heat resistance and durability. For these reasons, ceramics have long been used as insulators. Now let's see conductivity. Though fine ceramics are generally insulating materials that block electricity, semiconductor ceramics can be created to conduct electricity depending on their temperature and the level of voltage applied. So conductivity is a property that allows electricity to flow through a material. Fine ceramics are insulating materials in general, but some varieties exhibit electrical conductivity according to changes in temperature. A thermistor is an electronic component utilizes a property in which electrical resistance decreases as temperature increases, allowing electricity to flow more easily when the material gets hot. These devices are used in sensors that monitor temperature changes and in equipment designed to prevent electronics from overheating. A varistor is a similar component that possesses a property in which resistance decreases as voltage increases. Varistors are used to protect electronic circuits from excessive voltages. Now let's see electrical conductivity in metals. Electrical conductivity in metals is a result of a momentum of electrical charge particles. The atoms of metal elements are characterized by the presence of valence electrons, which are electrons in the outer shell of an atom that are free to move about. It is these free electrons that allow metals to conduct an electric current. Because valence electrons are free to move, they can travel through the lattice that form the physical structure of metal. Under the electric field, free electrons move through the metal much like a billiard balls knocking against each other, passing an electric charge as they move. Electrical resistivity, also called specific electrical resistance or volume resistivity, and its inverse, electrical conductivity, is a fundamental property of a material that qualifies how strongly it resists or conducts electric current. A low resistivity indicates a material that readily allows electric current. Resistivity is commonly represented by the Greek letter rho. The SI unit of electrical resistivity is the ohm meter. For example, if 1 meter by 1 meter by 1 meter solid cube of material has a sheet contacts on both opposite faces and the resistance between these contacts is 1 ohm, then the resistivity of the material is 1 ohm meter. Electrical conductivity or specific conductance is the reciprocal of electrical resistivity. It represents a material's ability to conduct electric current. It is commonly signified by the Greek letter sigma, but kappa, especially in electrical engineering, and gamma are sometimes used. The SI unit of electrical conductivity is Siemens per meter. The notation used for the Siemens is capital S. Now let's try to understand the electrical conductivity in metals with the help of a diagram which is shown in figure number 3. The conductivity of a material can be related to the number of charge carriers present in the material. Let us consider a rectangular block of length capital L and cross-sectional area capital A. Let small n be the concentration of the free electrons available in it. If a potential difference capital V is applied across a solid, it creates an electric field capital E in the solid is given by capital E is equal to capital V divided by capital L, where capital L is the length along which charge carriers move in the solid. Let's say this is equation number 1. The current capital I passing across an area capital A is defined as the net charge capital Q transported through the area per unit time. That is, I is equal to Q upon small t. Let's say this is equation number 2. The magnitude of the current flowing through the material is governed by Ohm's law. Let's say this is equation number 3. The resistance capital R is given by capital R is equal to rho into capital L upon capital A, where rho is known as resistivity. Let's say this is equation number 4. The reciprocal of resistivity is known as conductivity, that is sigma is equal to 1 upon rho, that is equal to capital L divided by capital R into capital A. Let's say this is equation number 5. Therefore, the total number of electrons in solid capital N is equal to electron concentration into volume. Hence, capital N is equal to small n into capital A into capital L. Let's say this is equation number 6. Now, total charge present in the solid, that is capital Q, is equal to total number of electrons multiplied by charge. Therefore, capital Q is equal to capital N into small e, that is equal to small n into small e into capital A into capital L. Let's say this is equation number 7. The current through the solid can be written as I is equal to Q upon small t, that is equal to NEAL divided by small t. Let's say this is equation number 8. Hence, the current equation capital I is equal to NEAV subscript D. So V is nothing but the velocity and subscript D stands for drift velocity, where Vd is the average drift velocity of electrons. So let's say this is equation number 9. Therefore, the current density is given by capital J is equal to capital I upon capital A. Let's say this is equation number 10. Hence, current density capital J is equal to, by simply putting the value of capital I, that is the current equation, NEAVD divided by A. So area that is capital A will get cancelled. Then finally we will have the current density capital J is equal to NEVD. Let's say this is equation number 11. Now Ohm's law, V is equal to I upon R, but R is equal to rho into L upon A. Hence I is equal to VA upon rho L, that is equal to 1 upon rho into V upon L into capital A. As E is equal to V upon L. Hence we can write current I is equal to sigma capital E into capital A. Let's say this is equation number 12. Now current density capital J is equal to I upon A is equal to sigma into E into A upon A. Hence capital J is equal to sigma into capital E. Let's say this is equation number 13. This equation is known as point form or microscopic form of Ohm's law. From equation number 11 and equation number 13, we can write the current density capital J is equal to small n into small e into Vd, that is equal to sigma into capital E. Therefore, the conductivity can be written as sigma is equal to NeVd divided by capital E. Therefore, sigma is equal to N into E into mu. Let's say this is equation number 14. In this equation, mu is equal to Vd upon capital E. In this equation, the quantity mu is known as mobility of electrons. Now let's see the definition of the mobility of electrons. The quantity mu is known as the mobility of electrons. It indicates that the ease with which electrons move in a solid. It is defined as the drift velocity per unit electric field. The unit of mobility is meter square by V into S. In metals, it is of the order of 10 raised to minus 3 meter square per Vs. And in semiconductor, it is of the order of 10 raised to minus 1 meter square per Vs. Now let us see the electrical conductivity in semiconductors. In semiconductor, the conduction band electron and valence band hole participate in electrical conduction. To obtain expression for electrical conductivity, consider an intrinsic semiconductor bar which is connected to external battery as shown in figure number 4. Let us consider a sample of semiconductor across which a DC voltage source is connected. If a potential difference is applied across semiconductor, it generates an electric field. This causes electrons to move towards the positive terminal and holes towards the negative terminal of the source. So as shown in this figure, capital L is a length, capital A is a cross-sectional area, capital V is applied potential difference, capital E is electrical field generated, capital I is total current. Capital I subscript small e is the current due to electrons drifting in the conduction band. Capital I subscript small h is current due to holes drifting in the valence band. Small v subscript small e is drift velocities of electrons. Small v subscript small h is the drift velocities of holes. Small n subscript small e is concentrations of electrons, and small n subscript small h is the concentration of holes. As shown in this diagram, the current due to the electrons is shown in red color with the arrows, that is capital I subscript E, whereas the current due to the holes, which is shown with the green arrows, which is I subscript H. So total current capital I is equal to capital I subscript E plus capital I subscript H. So total current is the current due to the electrons plus current due to the holes. Therefore, the electric field exists along x direction. The field accelerates electrons, that is conduction electrons, along negative x direction and holes along positive x direction. They starts moving with a constant velocity, which is called as a drift velocity. Therefore, the current due to the electrons is shown in red equation. Capital I subscript small e is equal to small n subscript small e into capital A into small v subscript small e. Let's say this is equation number 1. Now the current due to the holes, which is shown in green equation, capital I subscript small h is equal to small n subscript small h into small e into capital A into small v subscript small h. Let's say this is equation number 2. Hence, total current in the semiconductor due to both electron and hole can be written as I is equal to IE plus IH. Let's say this is equation number 3. By simply putting the values of equation number 1 and 2 in equation number 3, we can write I is equal to NeEAVE plus NHEAVH. So I is equal to EA in bracket NeVe plus NHVH. Let's say this is equation number 4. Now if mu E and mu H are the mobilities of electron and holes, hence mu E is equal to VE upon capital E and mu H is equal to VH upon capital E. Therefore, VE is equal to mu E into capital E. Let's say this is equation number 5, and VH is equal to mu H into capital E. Let's say this is equation number 6. Therefore, the total current capital I is equal to E capital A in bracket NeVe plus NHVH. Now simply by putting the values of VE and VH from equation number 5 and 6, we can write I is equal to small e into capital A in bracket Ne mu E into capital E plus NH mu H into capital E bracket complete. Therefore, I is equal to, by simply taking common capital E outside the bracket, we can write I is equal to small e into capital A into capital E in bracket Ne mu E plus NH mu H bracket complete. Let's say this is equation number 7. Therefore, the total current density capital J is given by capital J is equal to capital I upon capital A, where capital A is a cross-sectional area of the sample or the semiconductor. Therefore, capital J is equal to capital I upon capital A. By simply putting the value of current, that is capital I, we can write small e into capital A into capital E in bracket Ne mu E plus NH mu H bracket complete divided by capital A. So capital A will get cancelled. So we can write capital J is equal to small e into capital E in bracket Ne mu E plus NH mu H. Let's say this is equation number 8. If sigma is the total conductivity, then capital J is equal to sigma into capital E. Let's say this is equation number 9. Now comparing the equation number 8 and 9, we can write sigma is equal to small e in bracket Ne mu E plus NH mu H bracket complete. Let's say this is equation number 10. This expression, equation number 10, gives the electrical conductivity of a typical semiconductor. In general, it is linked to the variation of mobility with temperature is too small, and the large variation in electrical conductivity is because of large variation of electron concentration with temperature. Now let's see case A, intrinsic semiconductor. For an intrinsic semiconductor, the concentration of electrons and holes is equal. Thus, Ne is equal to NH is equal to Ni. Ni stands for the concentration in intrinsic semiconductor. Thus, the conductivity of intrinsic semiconductor, we can write sigma I is equal to E Ni in bracket mu E plus mu H. Let's say this is equation number 11. Now let's see case B, N-type semiconductor. The concentration of electrons is much greater than the concentration of holes in N-type semiconductor. Therefore, Ne is very much greater than NH. The majority of charge carriers are electrons and the contribution of holes is neglected due to very small value. Therefore, the conductivity of N-type semiconductor can be written as sigma E is equal to E Ne mu E. Let's say this is equation number 12. Now let's see the case C for the P-type semiconductor. The concentration of hole is much greater than the concentration of electrons. Therefore, Ne is very small than NH. The majority charge carriers are holes and the concentration of electrons is neglected due to very small value. Thus, the conductivity of P-type semiconductor is sigma H is equal to E NH mu H. Let's say this is equation number 13. Now, based on the formulae which we have discussed earlier for the electrical conductivity, resistivity, etc., let's see some problem solving. Example number 1. Calculate the energy gap of germanium given that it is transparent to radiation of wavelength greater than 17,760 angstrom unit. The solution of this problem is as follows. We have energy equation Eg is equal to h nu. Therefore, Eg is equal to h into C upon lambda. So by simply putting the values of all these parameters in this formula, energy gap Eg is equal to h is the Planck's constant. So 6.626 into 10 raised to minus 34 into speed of light 2.99 into 10 raised to 8 divided by the lambda value is given, that is 17,760 into 10 raised to minus 10, that is the angstrom unit, so it is in meter. So after calculating this, we get energy gap Eg is equal to 1.12 into 10 raised to minus 19 joule. So this energy is in joule. So let's convert it into electron volt. Energy gap Eg is equal to 1.12 into 10 raised to minus 19 joule divided by 1.6 into 10 raised to minus 19. So therefore, we got the value Eg is equal to 0.7 electron volt. So this is the energy gap of germanium. Example number 2. Calculate the energy gap of silicon in electron volt given that it is transparent to radiation of wavelength greater than 11,000 angstrom unit. The solution of this problem is as follows. We have energy equation Eg is equal to h nu. Eg is equal to h into C upon lambda. Eg is equal to 6.626 into 10 raised to minus 34 into 2.99 into 10 raised to 8 divided by 11,000 into 10 raised to minus 10. After calculating this equation, we get Eg is equal to 1.80 into 10 raised to minus 19 joule. So let's convert this value into electron volt. So energy gap Eg is equal to 1.80 into 10 raised to minus 19 joule divided by 1.6 into 10 raised to minus 19. So we get Eg is equal to 1.13 electron volt. Next problem, problem number 3. Calculate the number of acceptors to be added to a germanium sample to obtain the resistivity of 8 ohm centimeter. Given parameters mu is equal to 1600 centimeter square per volt second. The solution of this problem is as follows. We have resistivity equation rho is equal to 1 upon Na E mu h, where rho is the resistivity, Na is the number of acceptors, E is a charge on electron, and mu h is a hole mobility. Therefore, Na is equal to 1 upon rho into E into mu h. So simply rearranging the previous equation. Therefore, Na is equal to 1 upon 8 into 1.6 into 10 raised to minus 19 into 1600. Therefore, after solving this equation, we can have the value Na is equal to 4.876 into 10 raised to 14 per cc. Next example, example number 4. A germanium sample has 4.56 into 10 raised to 22 atoms per cc and a donor impurity is the ratio of 1 part per 10 raised to 10 is added to create an N-type semiconductor. If the mobility of charge carriers is 3900 centimeter square per whole second, find the conductivity of silicon. Therefore, the solution of this problem is as follows. First of all, the density of atoms in germanium, we can calculate 4.56 into 10 raised to 22 atoms per cc. So this value is already given. Therefore, the donor impurity is equal to 1 atom per 10 raised to 10 silicon atoms. Therefore, the mobility of charge carriers is equal to 3900 centimeter square per whole seconds. Therefore, charge carrier density, that is small n, is equal to 4.56 into 10 raised to 22 divided by donor impurity 10 raised to 10. So that is equal to 4.56 into 10 raised to 12 per cc. Thus, we have the conductivity equation sigma is equal to N into E into mu E. Therefore, simply by putting the values in this equation, we have value small n 4.56 into 10 raised to 12 into charge on electron, that is 1.6 into 10 raised to minus 19 into mobility is given, that is 3900. So after calculating this, we get sigma is equal to 2.849 into 10 raised to minus 3 mole per centimeter. Let's see another example. Example number 5. Calculate the conductivity of pure silicon at room temperature when the concentration of carriers is 1.6 into 10 raised to 10 per cc. The parameters are here given. Mu E, that is mobility of electrons, is equal to 1500 centimeter square per whole second. Mu H is equal to 500 centimeter square per whole second. Therefore, the solution of this problem is as follows. We have intrinsic conductivity equation sigma I is equal to E into Ni in bracket mu E plus mu H, where sigma is the conductivity, Ni is the number of intrinsic carriers, E is the charge on electron, mu is the electron mobility, and mu H is a hole mobility. Therefore, the conductivity of pure silicon is given by sigma I is equal to 1.6 into 10 raised to minus 19 into 1.6 into 10 raised to 10 in bracket 1500 plus 500, bracket complete. So after solving this, we get sigma I is equal to 5.126 into 10 raised to minus 6 mole per centimeter. So this is the conductivity of silicon. Let's see the last example from this topic, example number 6. Calculate the conductivity of germanium sample if a donor impurity is added to the extent of 1 part in 10 raised to 9 germanium atoms at room temperature. Given parameters are atomic weight of germanium is 72.6, density of germanium is 5.32 gram per cc, Avogadro's number is 6.022 into 10 raised to 23 per mole, and the mobility mu is equal to 3800 centimeter square per whole second. Therefore, the solution of this problem is as follows. We have the conductivity equation. Sigma is equal to Ne mu E. Therefore, number of germanium atoms we can calculate with the help of this formula. Avogadro's number divided by atomic weight of germanium into density of germanium in the crystal. Therefore, Avogadro's number is 6.022 into 10 raised to 23 divided by atomic weight of germanium 72.6 into density of germanium in crystal is 5.32. So after calculating this, we get 4.412 into 10 raised to 22 per cc. So therefore, there is one donor atom per 10 raised to 9 atoms of germanium atoms. Hence, small n is equal to 4.412 into 10 raised to 22 divided by 10 raised to 9. So after calculating this, we get 4.41 into 10 raised to 13 per cc. Therefore, conductivity is sigma is equal to Ne into mu E. So sigma is equal to n, the value of small n, 4.41 into 10 raised to 13 into charge 1.6 into 10 raised to minus 19 into mobility 3800. So after calculating this, we get sigma is equal to 0.0268 mole per centimeter. So this is the solution of problem number 6. This is all about electrical conductivity in metals and semiconductors. In my next lecture video, I will discuss upon Fermi energy, Fermi-Dirac distribution function, and position of Fermi level in intrinsic semiconductor. So please don't miss my next lecture video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's classroom channel to get the notifications about my upcoming videos. Thank you.